whatever that do the work, yeah, those things. So, by a show of hands, who here actually knows what a processor does?
Good question, I know it.
Yeah. Okay, that's not a lot of hands. Okay, so yeah, so I'm going to be talking about like basically just how like a basic processor works, and I'm going to be also be talking about two exploits that you might have heard about maybe last year that are pretty dangerous and pretty bad for everybody who has Windows 95 and anywhere past that. So yeah, it's really bad. Anyway, so I actually have a really easy explanation of how processors work. It's actually magic. You know, it just works. You know, and that's just how processors work. Actually, no, that's not really how they work. Processors are actually really complex units where they're made up of specific components that work together to basically do nothing. And that's really all the magic is here. You know, binary, like the ones and zeros, that gives you everything you need. It's kind of amazing. But anyway, so here's how a basic processor works. You can tell from the really bad display I have for my terrible projector. But what actually happens in a processor is you have a component called a program counter and instruction memory, where basically you just count through a list of instructions that are going to be executed by your processor. So you know that there's programming languages like that use assembly. Assembly is the lowest level language that you have besides machine code. And assembly is just basically a way of abstracting the ones and zeros that make up the encoded commands for your processor. So how a computer does that is it reads through a list of instructions that make up your program.
Hello.
So then once it's reading through each instruction, it sends that instruction into your instruction memory and part of the data path where it actually decodes your instruction to figure out what you're trying to do. So say if I have an instruction that I want to add two numbers, like say I want to do 2 plus 2, pretty easy operation. I would say, okay, I would like to have the assembly code for add, and I would like to add these two registers, which have 2 and 2 respectively, and I'd like to save that output into another register. So what would happen is the instruction will come out of the instruction memory and go into split into the segments to get the registers and go into the ALU. The ALU stands for arithmetic logic unit. So that's where all the math is done. So for our command, it would add 2 and 2 together and get 4. And that 4 would get passed into the data memory, and then since it needs to be stored into a register, it would go back into the register. So if you just follow these basic steps, this is pretty much how every single processor does its job, in the most basic sense of the idea. But the thing is, we don't have really basic processors like these anymore. Nowadays we have Intel processors that are capable of doing thousands upon billions of different types of instructions at once. And I think last time we checked, there's maybe 3,000 different instructions for Intel. For any specific Intel processor, it can range between 900 to 3,000. So that's a lot of instructions. But that's basically how the processor works. But it's a lot more than just doing that in sequence. You want your processor to run fast. You want it to be able to do a lot of instructions really quickly, and you want to see if you can make optimizations to make it work better. So there's a bunch of different methods that we use to make it run faster. So one of these methods includes pipelining. Now pipelining is a way where instead of saying, okay, well I'm going to add 2 plus 2, and I'm going to wait until that instruction finishes, and then I'm going to say, okay, well now with my 2 plus 2, I want to add my result to something else, and then go in order, so on and so on. But the problem is that would be kind of slow because we have multiple components that can do things at the same time that we're waiting for something else to finish. So what if we get all the things to run kind of concurrently and get my instruction memory to give out an instruction and then pass another instruction on at the same time. So while my ALU is doing 2 plus 2, I'm already working on the next instruction after that, which is doing my next part, which will then go and then get sent back to memory and then do all of that much faster. So the tasks that we have, instead of being like A, B, C, it will be stacked like together, like A, B, C, D, E, and that will be much faster to run all of those instructions. And that's one of the ways that we optimize the processor. But and this is kind of how it looks, where each little block is like the part that does a specific like part. Like we have the instruction memory, can pass to decode it, and then to do the math, put it into memory, and or like write it back to memory again. So it looks like a staggered kind of like display, but it gets all of your instructions done a lot faster. Now, there's a problem with doing optimizations because there was last year there was a few papers published about two new exploits that came into play. That at least I heard a rumor about that maybe the Intel CEO knew about before he dumped all of his stocks beforehand. Can I get a verification on that? No? Okay. But yeah.
All speculation.
It's all speculative, yeah. Speaking of speculative, that's part of the optimization process. So one of the exploits is called Meltdown. They call it Meltdown for melting down security boundaries. I kind of wish it did melt down the processor though, because that would make a lot more sense for the actual exploit. But it just melts down the boundaries in cache. So what actually happened here is because of that pipelining, because of the pipelining optimization that we did, the issue will become a problem of, well, what happens if I hit an exception and I'm not supposed to run a couple instructions ahead, but I'm already running a couple instructions ahead? That's where things will actually start breaking down. So it's called a micro-architectural flaw, where it basically means that if it's an architectural type, then it means that it will get fully passed through a pipeline. It will get fully passed through all the steps that it needs to take. But if it's micro-architectural, it will only take a few of those steps. So it won't be atomic in a sense. So let's have a little example to show how this works. So say I have a list of instructions, like instruction 1, 22, which are just generic instructions. But then I have, then say I'm an attacker and I want to get access to someone's other opened Chrome tab that conveniently has all of their credit card information stored in one nice contiguous or non-contiguous piece of memory, not calling out anybody's bank account like website things. So how would an attacker get past that? Well, if they want to abuse the pipeline, they know that they can't get direct access to that other process because the operating system prevents access to another process. But the cache doesn't actually prevent that. The cache is like part of the memory that gets a better lookup of like what you wanted to look up in memory. So if you ask, well, I want to get a piece of memory, a cache basically stores that piece of memory for like easier access. So that way I'm not asking for a piece of memory over and over again, and then having to look that up each time, because that wastes time, precious time that you can be using to actually solve your process. So if you keep reusing a piece of memory, then it get put into a cache, or at least the cache. Now the problem is we can abuse that. So what Meltdown does is it takes the instructions where I want to load in a piece of memory that I don't have access to, but it puts it after an exception call. So what actually will happen is instruction 1 will run with no problem, and instruction 2 will run with no problem. But I kind of have two arrows here. It's kind of hard to see. The blue one is like the line that's indicating that it's actually run completely, while the green line is indicating the one that's just started running. So if we get to the part where we actually need to raise the exception, the processor actually won't know it's a problem yet until further down the pipeline that it can't be actually run, and it should throw an error and then should trap and then go back up to the kernel mode where it will just ignore the instruction and not let it load memory from an illegal area. So, but the issue here is it's actually already starting to implement that instruction for the cache, even though the exception hasn't been called yet. So by the time we actually get to the exception, the processor has already, in the line, the memory has already been loaded into cache, and then the processor says, wait, stop, you can't have it, and then reverts everything else back, but the cache. So we still have the cache there, we just need to know how to get into it and take out the information from it. So what then is run is like a flush reload attack, where basically I just go through the, I just ask the processor, okay, I want you to load pieces of memory, even though I don't have access to them, but just load them anyway, just so I can, like, I don't know how it goes. So if you load all the pieces from memory, all the parts that aren't in the cache will be called a cache miss, and that will take longer for it to actually get passed into memory, because it has to load it first to check whether or not it's actually there due to the pipeline problem. But it will take longer to load that. Now here's where we actually win. If it's a cache hit, like if it's actually already, like the memory they already want to access already in the cache, it will finish the instruction like really quickly. We don't have to wait for it to actually go and access the memory. So that means I know when something is there. So what if I wanted to know what everything is in memory, but I didn't have access to everything in memory? I could just continuously ask the processor to load illegal parts of memory, and then I could just say, okay, well, I'm going to ask you to load that piece of memory, but add a number to it. And then while I'm asking you to read all the parts of memory again, if a number in memory suddenly becomes a lot faster to access, that address minus the number that I added to it is where the memory is stored. And then I could find out from that also what data is in there as well. And there you go. Using that, I can read what your bank account is, and I can find out what everything else. And so there's also another exploit called Spectre, which is another, like, basically kind of the same idea, but instead of using the fact that the pipeline allows you to like access things before they're run, processors have this thing called branch prediction, where say if I have like an if statement, right? But I don't know, I'm a bad programmer, or just something is always going to be like true in that if statement. What's going to happen is the processor is going to say, okay, well, this thing is like always true, and this like area is always being run like the same time, like always going to work. So I'm going to predict that next time he runs it, it's also going to be true. But the problem is, if you assume that it's going to be true, couldn't I also put something that you're not supposed to run after that, and then it will assume it's true and then run that thing I'm not supposed to run? Exactly. And there you go, stole your bank account again. So yeah, there's another way that's an issue. So the same idea here, we're just keep asking if it's true, and then using the same way that we were reading memory, like reading all of the addresses in memory before and asking for that information, we can deduce what's in there as well. And there you go. Now, so that is a really big issue. Now, it only gets even worse when you realize that this has kind of been in like every Intel processor since like the 90s. So how are we supposed to patch that? You know? So the thing is, like, you can't really patch it like in terms of like permanently fix it in terms of like a software patch, like where it like takes care of the problem like entirely. You can stop it from like running those like specific like predictions and stop it, but it won't be a perfect like process where you get the most out of your processor at the same time. So it's a give or take. You either have the vulnerability or you have a slowdown in your processor. Supposedly this can get up as bad as to like 3% maybe. Like in a very, very worst case scenario, 3% loss on your processor like output. So it gets pretty bad. Now the thing is, because you have to like come up with patches for like every single like version after that, or not for every version after, but every or pretty much every operating system to put a patch on top of that, you're never going to get it for this. So yeah. However, curiously, AMD processors don't actually suffer from this due to the fact that they have a specific type of like design for their pipeline. But they're still actually breachable by Spectre as well, because the Spectre one is not related to just like one specific pipeline. It's related to the branch prediction and other stuff. And since all processors are kind of implementing that, they're all vulnerable to that as well. So pretty much the only real way to fix this is to get a new processor that permanently fixes this, or has specific memory for private areas that it just can never get access to, or you can't ask the cache to load things that you're not supposed to load. There's different ways of trying to patch this, but those are the general ways. So if you really want to like prevent against this attack, you just kind of have to use a brand new processor. But at least this makes it good for me, because if I ever want to hack a Windows 95 machine, for example, I have a perfect entry into it. And the worst part about this is you could probably run it with JavaScript. Actually, you can run it with JavaScript. That's how bad it is. So, yeah. So yeah, everything can be hacked, even the hardware. So yeah, don't let your computer get destroyed by a JavaScript program, please. And install an OS patch, even though it's going to reduce your memory by like performance a teensy little bit. But that's why every part of like the processor, like every part of computer design is that much more important to making sure that you're preventing someone from getting you at like either the highest level, the lowest level, and anywhere. All right, thank you.
Apple is
Questions? Yes?
Apple is immune.
Anything beyond Intel or AMD? Any others that are?
There is ARM. There are ARM processors that are actually vulnerable. Only a few of them so far, but still some of them are actually.
What about RISC or Spark or some different architectures?
RISC-V? We're not. Depends on the implementation. Technically, if they do this, if they don't like actually put into like account these kind of exploits, then yes, they could probably be exploited on just the same way. So it can affect almost all
How
times.
about an old Spark chip?
For what?
Old Spark chip.
Spark chip? I'm not sure specifically.
Because
But
they use the other Indian.
There's got to be a list on the internet.
There are
all the
Right, it's its own
supposedly
proprietary
Infineon
instruction set,
processors
right?
are actually okay because they don't have to worry about like certain things about the pipeline part. But generally, like Spectre attacks, like of different kinds of types, can work. Just you have to know how to implement it.
So we've got four.
Yeah.
Not a question, but more of a comment, which is if you run a Linux system and you want to see your mitigation status, there is a vulnerabilities directory that will show your Spectre and meltdown mitigation, whether or not you're vulnerable to it. I don't remember what it is off the top of my head, but it's it's Etsy somewhere. No one runs Linux, okay.
Okay, so the thing is, you technically, because that everyone has already like worked on like newer patches to solve this, if you're running like nowadays like pretty recent operating systems and stuff, you're technically going to be fine, because if you install your updates and you keep track of stuff, then because like Windows and like other operating systems have made a very great deal about get this like update right now, or forcing you to, because that's just how they want to like take care of it. It's such a big problem. So technically, newer systems aren't really much to worry about. As for data centers, as long as they update, yes, because they're probably fine. And as long as they're not running anything like Vista or Separ.
For the predictability, is that just they created that just for saving time for running commands, and can they eliminate that completely and will it slow down like crazy?
You could technically eliminate it completely and go like instead of like doing pipeline, you can go back to single instructions and complete everything. And that would eliminate all the vulnerabilities. But yeah, you would get a really noticeable slowdown from pipeline to no pipeline. So, yeah, but there are a lot of different ways you can solve this. Some of them include just basically like limiting access to what people can do, stopping people from accessing the cache when they're not supposed to, and all the way to the hardware level of just making whole segments of memory so private nothing can access it unless it's actually advised that it's able to. It depends on the implementation of the process. Okay. Any other questions? Okay.